In this video, we're going to look at some practice problems related to finding the derivative at a point. Note that a lot of these practice problems are going to be similar to what we did in section 2.1, but now we're giving it a different name, and that is finding the derivative instead of the average and instantaneous velocity. So first example, estimate f prime of 1 given that f of x equals 2 to the x. So one reason that we're going to estimate this is that finding the limit, the actual definition of f prime of 1, that is the limit as h approaches 0 of f of 1 plus h minus f of 1 over h is difficult algebraically. So we're not going to be able to do that. So we are just going to estimate this instead. And we'll do that with a table. So we're going to choose values close to x equals 1 from either side to estimate the derivative. So let's look at, here's x equals 1. We're going to look at something just below x equals 1 and then something just above x equals 1. So let's look at x equals 1.0001. We'll go very close to it. And x equals 0.9999. In both of these cases, what we have here is h equal to 0.001 and h equal to negative 0.001. And since we're trying to find the difference quotient, then we only really need to deal with the value of h. So note that we are trying to find what the derivative is at x equals 1. So here we have x values. Here we have the derivative at the x values. We're trying to find the derivative x equals 1, and we're going to estimate it with the secant line close to it. So first thing here, what is the derivative when h equals 0.0001? Well, we're going to plug this into f of 1 plus h minus f of 1 over h. Note this is the secant line, the slope of the secant line is going to be f of 1.0001 minus f of 1 over 0.0001. So that is going to be 2 to the 1.0001 minus 2 to the first over 0.001. On the other side, and we'll find this in just a second, on the other side, we have f of 1 plus h minus f of 1 over h, and this is going to give us f of 0.9999 minus f of 1 over negative 0.0001, which when we plug into the function will be 2 to the 0.9999 minus 2 to the first, which is 2, over negative 0.0001. So the first value, when we had h equals 0.0001, when we plug that in, we would get a value at least close to 1.3863. And when we plug in negative 0.0001, we get 1.3862. So we might have that our answer is going to be the average of this, that f prime of 1 is going to be the average of these two numbers, or about 1.38625. So note that when we talk about estimation, there's a lot of freedom that we have in the problem. We could have picked h equals 0.1 instead of 0.0001. We could have gotten even closer to 1 than that. There's lots of different kind of freedom. This idea of doing something from the left and from the right is going to be important, and then taking the average is a nice way to do it. And that's going to be our go-to kind of strategy for this kind of problem. All right, so next problem here. Let's answer the same question. Find the derivative f prime of 1 of the function 2 to the x. This time we're going to use the graph of the function. So in this case, we're going to look at the tangent line and try to find the slope of the tangent line. So here is the graph of 2 to the x, and we are concerned with the derivative at 1. So I'm going to draw a sketch of the tangent line to the best of my abilities on what it looks like. And I am going to find the slope. I'm going to estimate the slope of this line. And that's going to give me an estimate for f prime of 1. So I'm going to pick 2 points. The one point that I know is 1, 2. When you plug in 1, you get a value of 2 out. And I'm going to pick the point, how about up here, which is about 2 and 3.5. All right, so we're going to have that f prime of 1 is going to be about 3.5 minus 2 over 2 minus 1, or in this case, 1.5 over 1, or 1.5. Note that on the previous page, we got an answer about 1.38, so we're a little bit further off. I think we can say that we are a little closer with the previous value because we went to more detail. But this is a rough approximation, just sketching the tangent line. So the next example, let's consider the function f of x equals x squared minus 6x. And we're going to find the exact value of f prime of 2. And in this case, we're not estimating, we're going to use the definition to find this. So we have that f prime of 2 is going to equal the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. So let's plug everything in. 2 plus h, we're going to plug in for x into the function. That's going to give us 2 plus h, quantity squared, minus 6 times 2 plus h. So all of that is just our f of 2 plus h here. Minus f of 2 is just going to be 2 squared minus 6 times 2. So that is f of 2. And we're going to subtract the entire thing. So that's why we need parentheses. And then divide by h. We said in the previous video that we can't just do this derivative or this limit right off the bat because this is going to be 0 over 0, which is an indeterminate form, which means that I need to simplify this algebraically in some sense before I'm able to find the limit. So let's do some simplification. We can FOIL some stuff out, cancel some terms. We have 2 plus h squared is going to be 4 plus 4h, 4 plus 4h plus h squared. We're going to distribute the negative 6 to both those terms. It's going to be minus 12 minus 6h. And then we have here minus 4 plus 12, distributing the negative to both terms. We distributed the 6 to both terms, negative 6, and we have everything over h. So next step here, we have equals the limit as h approaches 0. And we can cancel some stuff out. We know that we have a 4 here, negative 4 there, and a negative 12 and 12. And maybe at this point you're starting to see a pattern with these different quotient problems that everything without h cancels out. And that's a good check to see that you're doing these problems correctly, because that should happen, as we need a way to cancel out the h. And the only way we can do that is that everything without h actually goes away. What we are left with here is 4h plus h squared minus 6h all over h. And we can cancel out an h out of every single term. And we are left with the limit as h approaches 0 of 4 plus h minus 6. And now, we still haven't done the limit yet, but now we can plug in 0 for h, and we get 4 plus 0 minus 6, or negative 2. So when doing these limit problems, I want to bring your attention to the fact that I wrote equals limit as h approaches 0 every single step of the way until I actually evaluated the limit by plugging in 0 for h. Please do not skip on that notation, as if you do, you may be doing something that is incorrect, and mistakes can be made just because you leave out that limit. So last problem in this video, let's find the equation of the tangent line to the graph of f of x equals x cubed at x equals negative 1. So in this case, our a value is negative 1. And we know that the equation of a tangent line is going to be y equals f of a plus f prime of a times x minus a. So what we need to find, since we have a equals negative 1, we need to find the function value at a, and we need to find the derivative at a. So let's start with the easier question. Let's find the function value at a. That is f of negative 1. In this case, that's going to be negative 1 cubed, or just negative 1 itself. To find the derivative, that's going to be a more complicated problem. And again, we have to use our limit definition of the derivative. So f prime of negative 1 is going to be equal to the limit as h approaches 0 of f of negative 1 plus h minus f of negative 1 all over h. And we plug it into the function. That's going to give us a negative 1 plus h cubed. F of negative 1 is minus 1, so that's going to give us a minus negative 1, and then all over h. So we have some algebra to do. We have a cubic that we have to expand. We can do this maybe off to the side. How do we do negative 1 plus h cubed? Well, you may know a formula that you can do a cubic expansion, or you can write this as negative 1 plus h times negative 1 plus h squared, not squared like that, sorry, negative 1 plus h squared, and then do the squared first. This will be negative 1 plus h times 1 minus 2h plus h squared. And then finally we can write this as negative 1 plus 2h minus h squared plus h minus 2h squared plus h cubed. Rearranging the terms, this is h cubed minus 3h squared plus 3h minus 1. And if you use the formula for cubic expansion, you should have gotten that same thing. So, going back to our limit, we have negative 1 plus h cubed is going to be h cubed minus 3h squared plus 3h minus 1. Then we have a plus 1 from f of negative 1 all over h. We said that in these problems, we should always have everything without h cancel out. We do. We're going to write this as limit as h approaches 0 of h cubed minus 3h squared plus 3h all over h. And we can cancel out an h out of every single term. And we're left with the limit as h approaches 0 of h squared minus 3h plus 3. And now when I plug in 0 for h, we have 0 squared minus 3 times 0 plus 3. And our answer is positive 3. That's our derivative. So, plugging this in, because we're asking for the equation of the tangent line, our tangent line is going to be y equals f of negative 1, which is going to be negative 1, that's from up here, plus the derivative, 3, times x minus a, or x minus negative 1. And that's our answer. We could simplify this. We could write this as y equals negative 1 plus 3 times x plus 1. We could put this in slope-intercept form if you so wish. We could write this as 3x plus 2. But we have no need that we need to do that. We can just leave it in point slope form. So lastly, here's a picture of that tangent line, 3x plus 2, and the equation and the function itself, y equals x cubed. And we can see that it does match up at that special point, a f of a, and it kind of bounces off that function, and it's a nice line with a slope of 3. These problems that we're doing can seem very lengthy with all the limits. I urge you to not be lazy with doing those limits and do it step by step. Write equals limit as h approaches 0 each time. That's how you're going to prevent yourself from doing mistakes and you get more comfortable with dealing with limits.